All right, this will be our introduction to the graphs of secant, cosecant, tangent, and cotangent, as well as the graphing tool provided on our D2L page. So currently up on the board, we have the graphs of both secant and cosecant, with secant shown in red and cosecant shown in blue. Additionally, in the dotted lines, we have the graphs of cosine and sine, also in red and blue. So since secant is drawn in red, I have cosine drawn in red as well, since secant is 1 over cosine, making sine the graph that's drawn in blue, because cosecant is drawn in blue and cosecant is 1 over sine. So I want to draw some parallels here and draw attention to a few things that are somewhat interesting. Uh, Namely, that the maximums and minimums on sine and cosine become the local maximums and minimums on secant and cosecant. So I'm looking here at the points where secant and cosine intersect, right at that point 0, 1, or looking at the points where cosecant and sine intersect at the points pi over 2, 1. And we can see that pattern going all the way across both maximums and minimums. If I put away the cosecant graphs for a moment and just look at the graph of secant, even without cosine, secant is just the graphs of these U shapes, some of which open up and some open down. But the most important part of these 4 graphs that we're going to be looking at are their asymptotes. So if I put up some of the asymptotes for secant, they're shown here in orange, and they show up at all of the odd multiples of pi over 2, meaning the ones that are on the board are negative pi over 2, positive pi over 2, 3 pi over 2, and 5 pi over 2. And the reason these asymptotes show up at those values specifically is because they are everywhere that cosine of that angle is equal to 0, since dividing by 0 creates a problem. So with the graph of cosine put back on the board, we can see that each of those asymptotes occur where cosine intersects with the x-axis, because that's where cosine is 0. In addition to secant, I'm also going to put tangent up, since tangent would be the other trig function that has a denominator of cosine. And we can see similar things are happening here, where secant and tangent share the same asymptotes because they share the same denominator, which means they're both going to have trouble whenever cosine is equal to 0, which is what creates those asymptotes. So if we turn off cosine for a moment, or secant for a moment, and just look at the graph of tangent as it compares with cosine, we can see everywhere where cosine is 0, we have an asymptote for tangent, as well as maximums and minimums for cosine end up being zeros for tangent. Because wherever cosine has a maximum, sine will be equal to 0. And since tangent is equal to sine over cosine, anywhere where sine is equal to 0, we see that tangent also has a 0 at that point. But the graph of tangent looks just like what's on the board. It's that graph in green. And we can see that these patterns repeat between every asymptote. Whereas when we had secant up on the board, secant had a different shape every other asymptote. Sometimes they open up, sometimes they open down, which means we have to look between 3 asymptotes or a full period of 2 pi in order to get the entire graph or 1 full cycle of secant. To do tangent, we only have to look between 2 asymptotes, since every single time that same shape is repeated, which means that tangent has a base period of only pi, so just 1 pi, as opposed to 2 pi for most of the other trig functions. Once we get there, we'll see that cotangent also has a period of 1 pi. But enough about these functions. Let's go back to our graphs of cosecant and sine, back up here in blue. Now, cosecant has a different set of asymptotes. Namely, the asymptotes for cosecant should show up whenever sine is equal to 0. So we can see here at negative pi, 0, pi, and 2 pi are where we just have 4 asymptotes. So this tool is only set up to show 4 asymptotes, but there are an infinite number of asymptotes in both directions that we could find. But this tool is geared to work with your webwork graphs, so it'll only show this 3, it'll show 4 that include the 3 that you would see on any of the webwork problems you'd be working on. But again, we see that cosecant has its asymptotes whenever sine is equal to 0, since sine is the denominator of cosecant. And sine is going to be 0 at all of the whole integer values of pi. So 0, pi, 2 pi. We'd have another at 3 pi, although that's not listed. And also, if we go backwards, we find we have an asymptote at negative pi. X equals negative pi, specifically. Since all of these asymptotes should be written out as equations. For shorthand, it's easy to say that we have asymptotes at 0, pi, and 2 pi. But what I really mean when I say we have asymptotes at 0, pi, and 2 pi are I have asymptotes at x equals 0, x equals pi, and x equals 2 pi. It's fine colloquially, but anytime we're writing something down, we should be including the entire equation of x equals whatever number for each asymptote. So let's turn on the graph of cotangent to see it next to the graph of cosecant and sine. And we have it here in purple. And we see that cosecant also has the same asymptotes as cotangent. So, the reason for that being that both of these functions have a denominator of sine. So if we turn cosecant off again for a moment and just look at cotangent's relation to sine, again, we see that those asymptotes show up everywhere that sine hits the x-axis. So if we look at just cotangent without anything else except for those asymptotes, we see that same thing that shows up where we talked about tangent, that the graph of cotangent repeats its same pattern, its same shape between every pair of asymptotes. Meaning I don't need a full circle, I don't need the full 2 pi to look at one full period of cotangent, I only need half a circle, so just 0 to pi. And if we compare the graph of cotangent to cosine, we can see that again, cotangent has zeros in the same spot where cosine has zeros, since the numerator of cotangent is cosine. So each of those spots where we hit an odd multiple of pi over 2. Okay, so in order to use this graphing tool with, say, one of the problems on worksheet 8, I'm going to look specifically at problem 10 first, which is -9 cotangent of 4x minus pi over 7. I can use this graphing tool to get that graph. So since problem 10 is a cotangent function, I want to turn on my cotangent graph. So here's cotangent. And then I want to adjust those values of a, b, and c to get the right looking graph. So problem 10 has an a value of -9. So I'll take my slider for a and move it down to -9. I notice when I do that, it stretched the graph out quite a bit. In addition, um, it reversed the direction of cotangent. So in fact, the graph of negative cotangent ends up looking just the same as a graph of positive tangent. I'm just going to adjust the y-axis here for a moment. Let's make this go, how about up to 45 and starting at negative 44. That'll be good enough to get our shape to come back. Then we'll adjust for B and C. B has a value of 4, so we'll adjust our slider up to 4. Notice it's making those asymptotes bunch together. And then finally, we'll adjust our value of C to be negative pi over 7. It's going to be pretty close to 1/2. So we just kind of look at the slider for a moment. I went a little too far. 1/2 is about there. Let's just go ahead and type in an actual value here. I wanted pi over 7. And here we have a decent looking graph. We even zoom in a bit on that if we wanted to. There's our graph of cotangent. If we wanted just the part that's on the unit circle, so between 0 and 2 pi, adjusted for all of our values, I could choose this top value for cotangent instead of the bottom one, because it just restricts it to be one full circle. And again, it's set up to do a full circle, which means we're going to get more than one period for tangent or for cotangent. All right, so let's look at another example, and I'll jump ahead to problem 11. And problem 11 is looking at a graph of cosecant. So if I just reset this graph and turn everything off, again, problem 11, I'm looking at a graph of cosecant, so I'll turn on cosecant. And then I'll adjust each of my other values. A has a value of 4, so I'll slide this up to 4. You can see that's creating a fair bit of separation between the x-axis and those curves. So again, I'll just adjust my y scale a little bit. Just add 10 to both values. Next, we had 4 cosecant of 3x plus pi, which means that b is equal to 3. So we'll slide this over to 3. And again, that is scrunching up our graph quite a bit. Let's also go ahead and turn on the asymptotes for cosecant. It's one where bx minus c is equal to k pi. And then adjust this last c value over to pi. Let's see how close we can get. 3.15 would be close enough. And of course, I could go in and just type in a value of pi, but I think this slider is going to get us close enough. And so here we have a graph for that cosecant function. And zoom in a little bit as well. If we wanted to just get one full period. Once again, if I wanted just one period, I could turn on this top function that's restricting x to be within an adjusted 0 to 2 pi, which gives me just these pieces for cosecant. One upward facing segment and one downward facing segment.